So yeah, hopefully I don't disappoint after my talk last year. This one has far fewer graphs in it, but luckily it's still just as much vaporware. So, you know, I feel like with a talk title like Edge Compute the first 5,000 years, you have to kind of like, you all probably know what to expect. There's going to be lots of vaporware in here. So, right, so we started off today with like a talk from Mike Jones, right? And it was like an excellent talk, highly practical. And I kind of feel like that followed through with most of the talks for the rest of the day, right? Like there's a lot of really practical talks today. And I'm going to do the opposite of that. So like, I mean, actually, as it turns out, like Edge Compute actually does have quite a few like really simple, useful applications. However, the really interesting stuff comes later when you get into like crazy town. So we'll see. So hi, I'm Tyler McMullen. I am the CTO of this company, which basically just means I get to go around and give interesting, hopefully interesting talks and work on interesting problems. So a lot of fun. You can find me on Twitter right here. I love being told I'm wrong. And last year after the load balancing talk, lots of people told me I was wrong. And some of them were correct. So, right, so one of the reasons I wanted to give this talk is because Edge Compute has kind of a weird reputation. It seems like a new concept, but mostly it just seems to mean something different to everyone who I talk to. So when I was writing this, I kept starting and stopping and starting and stopping and starting over, despite the fact that I have a lot of thoughts and opinions on this thing. And I think part of the reason for that is that it's such a vague topic. Like, what do we mean by compute? What do we mean by edge? I guess it's like doing computations at the edge of the network. So, right. So I texted a good friend of mine. In fact, so he's an incredibly experienced developer. He's author and maintainer of things that we all use every day. In fact, multiple of his projects were like referenced in multiple talks today, which I'm always excited to see. But so I texted him and I was like, hey, what do you think Edge Compute is? And his response was this. You're an app store for HTTP requests? Or shitty middleware? I don't know. So we might have a marketing problem here. Right, okay, so Edge Compute is about moving computation close to the source. Right, what do we mean by the source? So this phrase is actually carefully chosen. The edge or the source has almost nothing to do with the physical topology of the network. It's not necessarily about like the physical edge of the network. It doesn't have to be like a mobile phone. It doesn't have to be like, you know, whatever is at like the very edge of like a star topology network. In fact, like depending on how you look at like the different topologies of networks, not all of them even have an edge, right? What we're actually talking about is by the edge is like the source of input to the system. It's like close to the thing that is generating and potentially also using the data. So in other words, like the edge is defined by the application, not by the network itself. I think this is like one of the most misunderstood things about like edge compute. So what we're referring to as the edge here really does mean something specific. It's not quite as vague as it initially sounds. The edge is the endpoint of the application. Cool. Like what? Cool. So airplanes are a great example of this. There are lots of computations happening in airplanes at all times when you're flying, right? So like takeoff, cruising, landing, like adjusting your like, I don't know how airplanes work. Basically it's its own little data center, right? So like apparently the Boeing 777 has like 3 separate PCBs, all of which are like formally verified and radiation resistant, which I didn't even know was a thing you could do. But like, just take a second and imagine if these computations were not moved to the edge of this network, right? Suddenly a like network split between your airplane and like AWS is causing you to like completely go off the rails, right? So, okay, another example. So like self-driving cars. This is kind of an obvious one. But even before self-driving cars came around, like there were lots of other things happening as far as like computations inside cars. Navigation systems, though I guess a lot of those are actually like just calling back to Google Maps. Sure. There's one more example. The JavaScript that we write is arguably also a form of edge compute. I know, I'm also skeptical of of the words coming out of my mouth. So like edge compute, edge compute is about moving computation close to the source of the data, right? So like when you are validating a user's input on the client side, how is that not moving the computation close to the source of the data, right? So like client-side sorting, client-side filtering, all of this is technically edge compute. The problem is this kind of edge compute is boring, right? Are you disappointed yet? Like, it's not boring because it's not useful. It's boring because it's kind of obvious, right? It's things that we've been doing for forever now. If you generate all the data that you need in order to compute a value in a single place, then of course you're going to move the computation to that place. Moving it elsewhere would just be kind of wasteful and silly. We've been doing this kind of thing since like the dawn of computation, right? And so the thing is that in the case of the browser and the validation example, like the edge compute we're describing is entirely stateless. It's stateless kind of in the same way that like a purely functional language is stateless. The validations don't have side effects. You know, they're not querying things and then like modifying state over here, which is going to carry over multiple requests. It's just, okay, input comes in, yes or no comes out, right? And the same kind of goes for the autopilot in a car and the autopilot in a plane and the self-driving car example as well. The other way is that, like, you know, alternatively, there are some examples that are not stateless technically, but are entirely trivially partitionable. So, for instance, in the case where you have that self-driving car that reports back, let's say, aggregates of like the sensors inside, right? So I guess like Teslas do this, for instance. The car is filled with sensors, which are constantly monitoring the state of all the different bits of the car. With some of them, they will build up aggregates of these stats as you're driving, and then they will like, you know, convey that information back to a central server. So in this case, it's not technically stateless, but the state that it deals with is only its own. It's trivially partitionable. So there must be a good reason for this, right? Like why don't we see other like edge compute applications that aren't this way? Like there must be something like hard about it, right? So there's a tension between moving computation to the edge and coordination. If you keep computation centralized, you have all the state available to you, right? But you also have to get all that state to the centralized system. If you move computation to the data producer, to the edge, you have instant access to it, but you also don't have access to any of the rest of the state that's happening around the network. Does that make sense? So for instance, imagine you were designing, again, the self-driving car example. Let's say all the cars on the road are like self-driving at this point. We're like in fantasy land now. If you were to design this as like a centralized system, you could pull all the sensor data from all the cars back into like one huge computer. You could run some like algorithms on it, and then you could just kind of drive all the cars in sync with each other, right? If you know everything that's happening, you can kind of like run the thing like a conductor of sorts. Like your centralized system is essentially like a conductor for the cars. But that's obviously completely unrealistic. You can't do that in the real world. So instead, all that computation needs to be done in each individual car, which makes the problem easier from the perspective that you don't have to move all that data around. But it also makes it much harder because you can't necessarily coordinate between all the different vehicles. So I guess edge compute is just, you know, useful but boring. That's fine. All right, before we write it off, and I have to like leave this stage in shame, let's go back to this notion of coordination. So if edge compute is at odds with coordination, then it's ideally a like coordination-free system. Right? Like, what is a coordination-free system? Let's see how this is. Okay, it works. Right. So let's talk about what a coordination-free system is not. That might make it easier. So let's say you have some kind of distributed system, and clients can write some kind of values to it. The specifics don't really matter in this case, so let's say we're writing unicorns. In this case, you want your system to be very consistent, let's say. You know, you want your unicorns to like all agree. And so in this case, you're going to like, you send out a broadcast when someone tries to write a value into your distributed system to tell all the other servers that you want to write a new unicorn. You get a couple responses back. There we go. enough that it's a quorum. So like 3 out of 5 all agree, yes, pink unicorn, we're into it. And only then do you respond to the user telling them that their unicorn has been accepted into Unicorn DB, right? So this is like the opposite of a coordination-free system. Nodes in a coordination-free system need to be able to make progress without talking to other nodes. That last example is like the complete opposite of that, where like in order to write a single value, you have to communicate with multiple of them. So like coordination-free, you need to be able to make forward progress without actually talking to anyone. So it's easy to see why this is like, or it should be easy to see, I think, why this is necessary for edge compute applications. You know, if your car needs to get quorum with all the other cars around it before it can decide to make a turn, you're going to be missing a lot of turns. So when you think about it this way, I think it starts to make more sense. It makes sense that the way edge compute is typically done is with only local data or completely statelessly, as in the case of like JavaScript validations. Because essentially what we're trying to do is build coordination-free distributed systems. That's what it actually is. Edge compute is coordination-free distributed systems. If you have no state, this is easy. If you have only local state, this is also easy. But the point is, like, coordination-free distributed systems, like research, should then apply directly to edge compute. Cool. You know, even if the current uses of edge compute seem kind of like obvious, we don't need to necessarily like look to research for edge compute advances. We need to look to research for coordination-free systems examples, which leads me to the realization that what we are in is like the Stone Age of this idea of edge compute. How many times am I going to say edge compute in this talk? I'm just realizing like it feels like that's all I'm saying. But this is where the exciting bits kind of begin. Because if we are in the Stone Age, like let's take a look and see what is coming next. Hopefully, and this is where like all the vaporware also starts. So like what we do now is technically edge computing, yes, but let's look at where we can go from here. So there's been like plenty of research, recent research in coordination-free systems, but one of the pioneers in the space was sensor networks. So let's start there. Sensor networks, like lots of applications. Basically, it's a network of sensors. So like cars, airplanes, nuclear power plants, farms, all the like IoT crap that we all now have. This is all like arguably like a form of sensor networks. It's a bunch of sensors that are all trying to like work together to aggregate some value, to like query some value, to like find something that is true about like the state of the world. You know, and some of these are like huge, right? They're like hundreds of thousands of sensors in an area. So, right, 2001, this paper was published out of Cornell. It's the Cougar approach to in-network query processing. So in-network processing means trying to do aggregates, trying to do query processing, and it's happening inside the network, right? Rather than like you have all these sensors and you pull all their data down to like one node where you do the computations, instead all the sensors are communicating with each other and they're doing portions of that computation inside the network itself, right? So like, there might be interesting things here. This paper describes the idea that in sensor networks, you often have partial results or results with errors, right? Or like uncertainty. So the idea then is that we ought to build systems where like the nodes or the sensors work together to find answers or eliminate errors, eliminate problems with the data. The thing that I found noteworthy about this paper though was that A, it was published in 1981, and B, IEEE Transactions on Systems, Man, and Cybernetics is kind of the weirdest conference name I have ever seen. Right. So, but all that kind of leads into like the kind of recent coordination-free distributed systems research that we see. My like favorite like go-to place for this is a group called ConflictFree. It's a large research project that's funded by the EU at the moment, and they publish probably some of the most innovative stuff on like coordination-free systems in a very long time. So I just want to kind of go through a couple of those things. So technically this one isn't actually from ConflictFree, but it's from ConflictFree's founder. So this is the paper that kind of, it wasn't the first paper on CRDTs, but it's the one that ended up kind of defining a lot of it. So the idea is that there's this type of data structure called a conflict-free replicated data type. And the idea with that is that you can always make progress on updating, on changing these data structures, and then merge them back together with other instances of it. So like, let's walk through an example. So an add-only set is probably the simplest possible CRDT you could have. So, right. So let's say these are 3 different nodes, and you're like making progress. You're like modifying the data structure on each of them. So like the first one and the last one both make modifications. One adds 1, one adds 2. Easy enough. Okay, now that one is going to merge with the second node. Okay, so that's easy enough. We just pull in that second value. Okay, now we're going to write a new value. So now the middle node sees 2, 3. The first node still sees 1. The last node sees 2. And then we can actually merge that all back together into like 1, 2, 3, right? So like this is a really, really trivial example of a CRDT, like the add-only set. The idea, though, is that this data type forms what's called a lattice. It's called a semi-join lattice. And the idea with that is that there's always a way to calculate a least upper bound, or a way to calculate a join or a merge function between 2 of these. You know, add-only sets are really easy because like the operations are always commutative, right? Like if you add the same thing in 2 locations, it just becomes one thing when you merge it together. The problem is like then when you start wanting to do more complicated things like deletion, then you need to start doing like causal metadata associated with CRDTs, and this talk is not long enough for me to talk about that. So that's like kind of a basic example of a CRDT, but the idea of that lattice applies to all of them, that there's always this way to merge them, and you can always make forward progress even if you can't merge them immediately. So building on that, one of the things that ScaleConf released recently, or a couple years ago at this point, this is also known as like the Swift Cloud paper. This paper describes the design of a like large scale, like essentially production ready, like CRDT database. Essentially what this ends up becoming is it's a database for edge compute. That's the idea with this. Finally, so another like one of the interesting advances lately is this thing called LASP. So Chris Micklejohn here has been working on this idea of having a programming language that has this idea of like eventual consistency of edge compute built into it. So one of the problems that we have at the moment is that everybody has like this, essentially the problem is that without languages, without frameworks, we're going to be kind of stuck doing all these boring stateless edge compute projects. And that seems like kind of a shame to me. So one thing that comes through when you're reading all of these papers is an interesting fact. The strongest consistency guarantee that you can get while maintaining that idea of like constantly being able to make forward progress regardless, like essentially coordination-free distributed systems, the strongest guarantee you can make is something called causal consistency. So what does that mean? Well, let's walk through an example. So we have 2 actors in this example, Jack and Jill, right? So in this case, like we'll start out just by saying like there are events. Jack does A, whatever A is in this case. I don't have like unicorns in this slide, unfortunately. Jack does A. Jack then replicates A to Jill, right? So now Jill sees A. Jill does B. And so it's very clear then that A happened before B. Like that's kind of the important relationship in causal consistency, is this idea of like happened before. Is that like, is this like familiar to anybody here? Happened before? Yes. Seeing head nods, hell yeah. Right, so A happened before B, so B then happened after A. Jill replicates it back to Jack. Jack does C. Jill does D. So in this case, we then know that B happened before C. B also happened before D. We replicate back and forth. And so we see that C is now concurrent with D, right? Those are like the important relationships in like causal consistency. So how does that, so that's how causality works, right? But like what does that actually get us? What causal consistency gets us is preventing causally impossible states. So like let's walk back through this with real operations and hopefully see what I'm talking about. So let's say in this case, they're not just like random events here. We're going to say that Jack inserts X. Jack then replicates that to Jill. Jill is going to delete X because Jill hates Jack. That's fair. I hate Jack as well. Right, Jill replicates that back. Jack inserts Y, Jill inserts Z. Right. So, and then we can see that like when you replicate them back and forth, like they converge to the same value. And that's fine. The more interesting bit with this is what the possible states of the system are before they are finished converging. So with causal consistency, what you get is like, okay, you can have the empty state where they both start out. You have the state where Jack has written X. You have the state where Jill has deleted it. You have the state where like Jack has inserted Y. You have the state where Jill has inserted Z. Right. But what you don't have are these impossible states. There is no possible way of like dissecting that causal history where X coexists in this data structure along with Z, or where X coexists along with Y. So the idea with this is that causal consistency attempts to like model real world causality. You know, and just as like in the real world, like things can happen simultaneously. And so like causal consistency allows for that. But like the interesting thing with this is that it's still like, that's still a fairly powerful guarantee to be able to make. And so if that is the strongest that we can do in an edge compute world, that's still like potentially really interesting for us. So, right, causal consistency, like the time on the wall, like the wall clock time, doesn't really help you when you're building distributed systems. As like, even if you could definitively say that event A happened before like event B, like on the wall, like on the wall clock, like that doesn't actually tell you whether A caused B, or if they're like unrelated causally. In order to do that, you need to track the causality and develop a strategy for what happens when A happens before B, what happens when B happens before A, and what happens when they're concurrent. I hope that's clear. So the interesting thing is that like causal consistency is like kind of fundamentally at odds with the way we build systems today. Why? So why is it so hard to build systems that are based on this rather than based on something else? The problem is this thing called single system image. Single system image is an abstraction. It says that a distributed system, regardless of the number of nodes it's running on, regardless of where those nodes are, regardless of what's happening behind the API for this thing, it says that to the outside world, it should appear to be one system. It should essentially appear to be one single machine. And like this, the pursuit of this like single system image idea is why we have concepts like leaders in distributed systems. Because another way of describing single system image is to say that the system is essentially serializable. Meaning that to like an outside observer, it appears that every event in the system has a like specified total order. Like every event happens before one event and after another event. There is no like concurrent thing. And so everything happens like in step, one event after another, which is totally not how the real world works. Lots of things happen concurrently. So the problem is like once you start running your systems across data centers and across regions, and sometimes even like in a single data center, honestly, you have to grapple with the fact that single system image or serializability is not usually a realistic thing to do with large-scale distributed systems. I feel that it's like this relentless pursuit of this single system image idea that leads us to bad, hacky distributed systems designs. And what honestly in some ways makes distributed systems so hard. And so when it comes to edge compute though, like the idea of single system image just does not actually work at all. And it's why we see like the edge compute applications today being stateless, right? Because if you don't have a database that's single system image that's going to work across all this, like how are you going to build more complex applications? And that's essentially why we need like new concepts, new frameworks. So as I was writing this talk, I was reminded that a friend had written an article exactly about what I was just talking about, so I felt like I should probably actually just put it up here because I feel like a jerk for stealing his ideas. And in retrospect, I probably should have just like put all of his stuff up on the screen and just like peeled out. But right, he describes this as, we posit that striving for distributed systems that provide single system image semantics is fundamentally flawed and at odds with how systems operate in the physical world. So essentially, that is the ultimate problem that we're talking about. So what we need are new frameworks, new models, new concepts. You know, the part of the conversation that seems to be like missed currently, especially in conversations in industry, is this. The fact that like it's hard to build like complex edge compute systems. So I keep seeing edge compute discussed, but it's discussed in this way where it goes, we just have to move parts of the application out to the edge. It'll be fine. It's going to be awesome, you guys. We talk about new services, we talk about like applications even, but we don't talk about the part that's missing, right? So like even in like academic realms sometimes. So like this is the IEEE like computer magazine last year. This part, like it was essentially discussed as like a minor side note on the last page after breathless praise of edge compute for multiple pages. But like the lack of this by itself has the potential to sink this whole idea of edge compute. So that's a bummer. But let's talk about the future or whatever. Okay, so let's say that we do manage to address the lack of tooling. Let's say we address the fact that we'll need to convince many, many programmers to abandon their ideas of single system image, and we embrace causal consistency. What does the future hold for us then? So, write spikes can be handled just like read spikes. So, like if you want to handle like large amounts of reads right now, you do what? You cache it. You use a CDN, you use memcache, you use whatever, right? So with a causally consistent system, you can actually do the same things to absorb write spikes. Because if you don't actually have to immediately spread those writes across the entire system, you can actually have them buffer. You can have them like individually, like you can spread out the load of writing into your system across many machines, which is something that you can't really do right now in a serializable system. Additionally, network splits become an annoyance, not a crisis. So net splits in a causally consistent in an edge compute system would cause reads to become stale for a period of time, but it would not cause inconsistency and it would not necessarily cause like actual failures, which is pretty awesome. You also, ta-da, you get offline operation automatically. Because what is offline operation if not just a really long network split? And you get magical space unicorns. So like, I don't know, we have a long way to go until we get here. So, I mean, right. I always do this at the end of talks. What was the point of all this rambling that I just did? So like, despite all my ragging on it, edge compute is actually pretty exciting. The applications we're finding for it today are incredibly useful, but they're really just like scratching the surface. We are, again, in like the stone age of edge compute. Like, to push it beyond the relatively easy applications that we have right now, though, we need to look to other forms of research. We need to look to like sensor network research. We need to look to coordination-free systems research. And we also need new frameworks. And really more than anything else, in some ways we need new metaphors, which sounds really weird coming out of my mouth. But like we as programmers are so incredibly reliant on metaphors for things. We have objects. We have like the single system image idea. Like unless we come up with good ones for causal consistency and for like edge compute, it's going to be really rough going. And right, one more point that I'm supposed to mention is that Fastly is now launching our first South Africa data center. So. Yep, that should come up in a couple weeks, and I am super jazzed about it because it'll give me even more excuses to come back. Thank you. Happy to answer questions if anyone has them.
So I'm curious what you think the best example of a current edge compute implementation like in today's world would be. Like something that we're potentially using or interacting with.
Best application today. Well, so, I mean, arguably, if you're using a CDN, it's kind of, no. Like, I think honestly, like, honestly, I think like some of the coolest stuff is actually with like the self-driving cars. Because they are actually working together with a like centralized computer system as well, but they are doing a lot of the computation like offloaded to the car itself temporarily, which then communicates with like a separate system when it has to, right? So it does have that kind of like that. It's not actually causally consistent, but like it has that same sort of thing going for it. That's my favorite example.
Are blockchain distributed ledgers a form of edge compute?
Distributed ledgers. I'm not actually sure if that would be considered this. I mean, that's right. Like I ended up in a conversation like last year with some of the creators of CRDTs, and we ended up getting into this conversation about whether or not Bitcoin was a CRDT. And I don't remember where we ended up landing on that, but I think it kind of applies in a weird way. Yeah.
So I don't know how many systems you built using CRDTs or that sort of thing, but a lot of when you rely on a single system image, it does a lot of nice things for you.
Yeah.
So for instance, you don't get dirty reads or stale reads. They're all really nice properties. How do you envision dealing with those in an actual production system? Because it offloads a lot of the hard things to the developer to deal with that at the moment you can rely on your DB transaction or whatever to do for you.
Yeah. No, I think that's exactly the problem that I'm talking about here, right? The fact that it is incredibly hard for developers at the moment, especially when you're used to that single system image idea. Like the idea of moving to a causally consistent system is kind of like, oh God, how is that even going to work, right? Like we actually that's why we need more frameworks. That's why we need more concepts, more metaphors for this. But yeah, I don't have the answer to it, but a lot of the research that is coming out right now is specifically designed to approach this problem, right? So LASP as a language for distributed causally consistent computing is potentially pretty cool for this.
All the drone swarms we love to watch on YouTube, are those done in the drones themselves, or is that centrally done?
I have no idea, but I would love to find out.
Can I go? I'd be interested to hear your thoughts on whether it would be a useful thought pattern to think of causal consistency as a subset of eventual consistency thinking that makes it easier.
Yeah, so causal consistency is definitely a form of eventual consistency. In fact, with CRDTs, I think it now has a special designation of strong eventual consistency. So mathematically provable to be eventually consistent. Yeah, so the problem is I don't think that referring to it as eventually consistent actually helps developers to understand how exactly it will work, other than to say that you should expect to get stale reads. So I'm not sure. I would love to talk about it afterwards, though, because if you have ideas, I'm all ears.
So you're talking about all of this in the context of distributed systems. Is this actually similar to things like the C++11 memory model, where you have causal consistency between threads in a program?
Yeah, actually, it is very, very similar to that. That is exactly the idea behind it. It's kind of a shared term between the two. Yeah.
So are we trying to model what happens in the real world? Because I'm assuming if you're computing at different nodes at different points, the information you have available will create it could be different across different nodes based on the information. And when you aggregate those aggregates, you start creating actually quite a different outcome than trying to approach things in a linear, time-based fashion, which is consistent.
That is
so your aggregation, depending on which nodes aggregate at time, actually creates a different output, and maybe that's where it won't be consistent, because it's all about...
I think I missed the last sentence there. What was the actual question?
No, I'm just trying to understand if we're trying to model what happens in the real world is it's about which nodes aggregate at a different point in time, rather than can we take events and just linear them, play them back on top of each other.
Right. So, I mean, essentially what it's about is dealing with the fact that, when you are dealing with edge nodes, when you're dealing with things that are operating at the edge of a network, it suddenly is not possible to pretend that everything happens one after another, right? You have to actually address the fact that things can happen concurrently. And so again, it's just the fact that the strongest guarantee that you can get with that is causal consistency, where you go okay, this definitely happened before this definitely happened after this, or these two things happened concurrently, and I have to somehow deal with that.
Hi. The question has been asked about distributed ledgers, but I think there's some parts of the blockchain algorithm that's still kind of relevant here, like consensus consistency. If you don't necessarily have the part where you distribute to the distributed ledgers. Is that relevant?
I am not entirely sure. I'm not like super familiar with distributed ledgers, unfortunately. It's one of those things I've actually like intentionally avoided. I've like kind of been waiting for all of the like the hype to die down, and then I'll figure I'll like read the Wikipedia page. It'll be all right. All right. Thank you very much.
Thanks.